The use of composites has been increasing in today's world due to their superior mechanical properties, such as lightness, low density, and high strength-to-weight ratios. Within the composite, the use of fiber-reinforced plastics has seen a strong growth in sectors like aerospace, marine, wind energy, and automotive industry. The market for fiber-reinforced polymers is growing at a compounded average growth rate of 7% and is expected to reach $200 billion by the year 2032. The fiber-reinforced plastics can be broadly classified into carbon and glass-reinforced plastics. This growth also presents a challenge, as the durability of these products hinders their recycling once they reach their end-of-use phase. Currently, the majority of these products end up in incinerators, landfills, or in energy recovery processes. This not only destroys the value of the fiber materials, but also harms the environment. The production of these fibers is an energy-intensive process as well, which makes their recovery a necessary step in the direction of environmental protection. Recycling of fiber-reinforced plastics has been a topic of discussion over the past decade, both in the scientific community and at industry and policy levels. The challenge here, however, is double. Currently available recycling processes either consist of size reduction processes, such as mechanical recycling, or thermochemical processes, such as pyrolysis or solvolysis. These alternatives come with their own challenges. While mechanical processes are tried, tested, and scalable, they tend to reduce the dimension of the fibers to a subpar quality, making it difficult to reintroduce the material into high-quality products. On the other hand, the thermochemical processes that exist today are energy-intensive, and their process costs are not competitive compared to virgin fibers, especially in the case of glass fibers. Considering the problems created by these end-of-life products and the current difficulties in their recycling, we see an opportunity in the exploration of new pathways and recycling processes. One of the processes that has been discussed in the scientific community is electrodynamic fragmentation, also known as high-voltage fragmentation. Invented in the 1960s, the process of high-voltage fragmentation was initially conceived as a process to extract minerals from ores and has since been used successfully in the mineralogy sector. Since the process is based on the relative permittivity and dielectric breakdown of material, the process has been used to attempt the recycled composite waste such as incinerator bottom ash, printed circuit boards, photovoltaic panels, as well as some examples of carbon and glass fiber reinforced polymers. The advantages of this technique are that it limits the size reduction of the fibers and it results in effective separation between different materials. The high-voltage fragmentation machine features a modified Marx generator and a series of capacitors that convert traditional electrical current into high-voltage current. These components can adjust the voltage using nitrogen pressure, generating a rapid current ramp-up with peak rise times under 500 nanoseconds. The material to be treated is placed inside the process vessel within the processing chamber, located at the front of the machine. High-voltage fragmentation is a wet process as the material is treated in water or deionized water, utilizing the higher dielectric strengths of liquids compared to solids during fast ramp-up times. At times less than 500 nanoseconds, solids break down more easily than liquids, allowing the liquid to act as a dielectric medium. This phenomenon is known as electrodynamic breakdown. Several parameters can be controlled, in particular the voltage, ranging from 90 to 200 kilovolts, the number of pulses, the distance between the electrodes, from 10 mm to 40 mm, and the frequency of pulses, up to 5 Hz. The whole process relies on the principle of electrodynamic fragmentation. When the current ramps up within a time span of less than 500 nanoseconds, a plasma channel arc is generated between two electrodes. This plasma channel targets the solid sample placed for treatment, as the dielectric breakdown strength of solids is lower than that of the surrounding water medium. Temperatures around 10 to the 4 Kelvin degrees and pressures ranging from 10 to the 9 to 10 to the 10 Pascal are produced, creating localized shock waves within the solid sample. These shock waves propagate through the solid, focusing on weak spots located at the phase boundaries. This allows to obtain recyclates that are of better quality than those recycled mechanically, at process costs that fall between those of mechanical and thermochemical processes. In this video, we have presented the challenges that arise from composites recycling, and we have seen how the innovative process of high-voltage fragmentation, based on the principle of electrodynamic fragmentation, can be a possible alternative solution in treating composite waste.